Okay, yep. So I'm Alison Smith-Renner. I'm a very recent PhD graduate from the CS department. My dissertation research focused on transparency and control in interactive machine learning. So I'm really excited to be here talking about this work. I'm also part of a machine learning research group at Whitney, Bradley, and Brown. And today I'm going to talk to you guys about humans' perceptions and experience when interacting with or controlling ML models. Okay. And this research was performed with my collaborators, Leah, Jordan, Kevin, and Varun. All right, and we've talked about this a bit, so it shouldn't be a surprise, but machine learning is not perfect. We can't and shouldn't trust these systems to act autonomously, so end users, sorry to use that word, need to interact with these systems, whether for evaluating models, such as to determine if they're accurate or biased, for determining whether to follow or ignore recommendations, or for providing feedback to guide or improve these models. And this talk is going to focus on this interactive feedback or interactive machine learning, where a user or a human in the loop iteratively improves or adapts a model. And specifically, I'm focusing on the concept of control in interactive machine learning, which refers to the ability of the user to change or influence a machine learning model. And most prior research on control really explores whether or not users can provide input, or which control mechanisms or how much control is supported. But what about what models do with that input? So in interactive machine learning, these systems typically need to balance the user inputs as well as faithfully modeling the underlying data, which means that some shared control is necessary, and systems sometimes incorporate user input in unexpected or unpredictable ways. So in this talk, I'm going to explore two additional dimensions of control related to whether models incorporate user input as expected. And these dimensions are adherence, or how well models incorporate user input, and instability, whether models make any other unexpected changes when they update. And to better understand adherence and instability, we performed a series of user studies where we have non-machine learning experts interacting with the system for understanding and organizing large amounts of text data. So this too much text data problem exists in a number of domains, such as journalists who need to review lots of reports surrounding breaking news, or perhaps a customer service department who wants to triage their different complaints. And the approach that we use is topic modeling. So it's a common unsupervised approach for modeling text without predefined labels. It takes a collection of documents and generates a topic model that organizes the collection into the topics or themes that the documents are about. So for example, suppose you have a corpus of news articles from sports, crime, and technology sections. And within these documents, there are groups of words that appear together more or less frequently, such as the words base and run, which will appear in more documents about baseball, and Apple and device, which appear in more documents about the iPhone. And then also, documents are typically about multiple topics. So a document might be 60% about the iPhone and 30% that there is an expected announcement for it, and so on. So topic modeling captures this intuition by modeling each document as a distribution of topics, where each topic is a distribution of words. So topic model outputs are not perfect. They can be low quality or might not align well with how end users understand the data. And an algorithm expert can tune algorithm parameters, specify number of topics, or perform a variety of pre-processing methods. But what about non-algorithm experts? So we can't expect the average end user to understand how to tune parameters of the algorithm, but these non-experts do have domain knowledge about sports and locations that we want them to be able to incorporate into the model. So for this, we use an approach called interactive topic modeling. This allows non-expert end users to control model generation by interactively refining the model as it's being generated, such as by adding or removing, merging or reordering words and topics. So imagine we have these two topics in an initial model, and an end user might look at the location topic and decide to merge the words San and Francisco to make San Francisco. And in the baseball topic, she may want to add additional baseball words like out and inning, as well as move the word baseball to be the first word in the topic. And users can perform this interactive refinement until the model is high enough quality or better matches their expectations for the data. But updates in interactive topic modeling can be unexpected. So a user's changes might not always be incorporated as they specified, which we call lack of adherence, and small changes to a model can propagate in unexpected ways, which we call instability. So remember from the example, the user created the merged word San Francisco in the first topic and added words and moved a word in the second topic, but the resulting model might not be exactly as expected. So we might see that California was added to the location topic, which no longer contains Cincinnati, and strike may have been added to the baseball topic, which no longer contains coach. Also, baseball could show up in the second position instead of the first, which the user had specified. So a goal of these studies is to understand whether users notice and are affected by these unpredictable controls. So ITM, or interactive topic modeling, is a particularly good case for exploring adherence and instability because it is inherently transparent in that users interact directly with the underlying model representation. They see immediate updates and therefore are acutely aware when these unexpected changes occur. So in interactive topic modeling, we consider controls to be easy to validate. And you can contrast this with something like a recommendation system where users are unlikely to really even be able to perceive how their input affects the system. And in that case, the controls are difficult to validate. So prior work has looked at for difficult to validate controls and found that users really just want control, regardless of whether it actually does anything. They feel better being able to provide their input even if they don't notice an effect. So in our study, we're going to look at how that compares for controls that are easy to validate. Okay, so for these studies, we designed an interactive topic modeling system following a human-centered design process. We worked with end users to determine how they want to be able to refine topics, and then implemented their desired refinements on top of a common topic modeling algorithm called latent Dirichlet allocation. And I'll go into the details on that here, but here is the user interface we developed for our system. So on the left is the topic list, and on the right is the topic panel for the selected topic showing its top 20 words and top 20 documents. And users can refine the model by simple interactive mechanisms like clicking X to remove words or documents, or clicking in the input area to add a new word to the topic. So we first performed an exploratory Think Aloud study with 12 users to understand their experience and perceptions when interacting with our system. So we had 12 non-machine learning expert participants, and we topic modeled a data set of tweets that are complaints about air travel. And then users were asked to think aloud while using the topic model to organize the tweets into different types of complaints, such as lost luggage or delays. And they were asked to talk aloud and given 20 minutes for this task. And then afterwards, they rated their agreement with statements about adherence and instability, among other characteristics of the system. So first, let's look at the user's perceptions regarding adherence and stability. For adherence, the majority of participants agreed with the statement that the refinements they made were applied as expected. So in our case, the majority of users felt the system adhered to their inputs. And for stability, we asked participants their agreement with no changes other than the refinements I made occurred when I clicked update. And we can see that participants had mixed reactions on whether they noticed this system instability. And looking at their user reactions to unpredictable control, surprisingly, we saw both positive and negative reactions. So for a case where the system did not make a change exactly as specified, or there was a lack of adherence, this participant was frustrated because they thought that the change word order operation was uncontrollable. But in another case where the system did adhere to the input, when a participant added words that were given high priority, she noted that, well, she could be wrong, so the system should have some leeway. And in this case, full control was not preferred. For another case where the system made other changes than specified, or where the system showed instability, on the positive side, one participant said this made the model better, whereas on the negative side, another participant described a scenario where they were happy with the topic until an update changed it, and now they're unhappy. So to summarize from this initial exploratory study, we found that participants noticed adherence, but were mixed on whether they noticed instability, and that they had positive and negative reactions to unpredictable controls in general. So next, we built on the findings from this study to explore whether users notice differences in adherence and instability between different modeling approaches, and also to understand how they're affected by these controls in more detail. So for the second study, we compared 3 distinct topic modeling approaches for our system, which vary how input is incorporated to the model, either through informed priors or constraints, and how inference is performed, either through variational inference or Gibbs sampling. So these modeling approaches give us different adherence, stability, and update speeds. And in our study, the variational inference algorithm was more stable than Gibbs. Informed priors with Gibbs provide the fastest updates, but all update times were quite slow. We'll see reactions to that later. And the informed priors provided higher adherence than the constraints. So for the second study, we recruited 100 participants from the Upwork platform, and we chose Upwork instead of Mechanical Turk to try to get more motivated users. We randomly assigned them to one of the 3 modeling approaches, and each user got a unique model, and they performed the same task as the previous study, where they refined the model to organize the tweets into different types of air travel complaints. And this time we gave them 30 minutes for the task. And then afterwards, participants responded to closed and open-ended questions on their perceptions and experience with the system, including what they most liked and disliked and what was unexpected for them. So first, let's look at adherence. So participants in general thought the 3 systems adhered to their input, but users in the constraints with sampling condition did give significantly lower responses for adherence, which also aligns with the fact that this condition had lower computed adherence than the other conditions in the study. And for how users were affected, recall that in prior work found that users didn't notice or care what happened to their input when they couldn't validate it. But in this study, lack of adherence was the second most disliked and the most unexpected of the system characteristics. And in particular, we found that refinements that did not work as expected were less popular than those that did. So this shows us that in this easy to validate case, adherence is important to consider. So it's not just giving the control, but what the system does with it. Now let's look at instability. So participants were mixed on whether they noticed instability, while the informed priors with variational had significantly higher computed stability than the other conditions. Perceived instability was not impacted by condition. And also, as in the prior study, participants seemed polarized by instability. So for example, one participant said they didn't expect the words to update after adding a new one, but that they thought that was cool. While another said, I removed a word and saw it in a later topic, that's bad machine learning. So these findings again suggest that users might be willing to share control when models update with high quality or reasonable changes, but they'll be frustrated when they don't agree. So to summarize, participants disliked lack of adherence second most, behind only the slow updates. Instability was polarizing in that some participants liked it when it surfaced interesting information while others did not. And across the modeling approaches, participants differed only in whether they noticed adherence. So in closing, these studies highlight a need for us to better understand how users expect machine learning systems to adhere to their input and how to manage such expectations appropriately. And from our studies and related work, we argue that while users want to be heard, they want controls, they might be willing to share control with a good machine teammate. So we know that users want and need to be in control, but machine learning systems must balance user inputs and faithfully modeling the data, which means some form of shared control is necessary, and users might be okay with this based on our studies, which expose that this unpredictable control can be polarizing. So thank you, and I'd love to open this up for discussion.